Hello, good evening. The last session ended abruptly with the topic on flux. So, what we'll do now is continue with that topic. As I was telling you, flux, it's E dot delta S, where we already know E is the number of field lines passing perpendicular through unit area, delta S being the whole area. You take the product between the two, you will have the total number of electric field lines passing perpendicular through a given area. This is what I showed you. The number of field lines passing per unit area was called the electric field. This multiplied by the total area, that is delta S, will give you the total flux phi. And because we are taking the dot product, we know flux is going to be a scalar product. Theta is the angle between the two vectors, electric field and the area vector. Like in my last session I told you, this area is going to be a vector and the direction of the vector is always perpendicular to the area and outwards. So if you have an electric field pointing away from me, if this is a positive plate and I have a negative plate away from me, the electric field lines are passing towards you, meaning away from me. And if I keep an area like this, the area vector is also pointing away from me, perpendicular. So the electric field and the area vector both are in the same direction, in which case you will have theta equal to 0. So E dot delta S into cos 0. Cos 0 is 1. You will have the maximum flux passing through this area. On the other hand, if you have your area vector placed like this, your electric field is pointing away from me, but your area vector is perpendicular like this. So area vector and electric field both being perpendicular to each other, theta becomes 90, cos 90 is 0. So there is no flux going through an area placed like this. If the field is like this, there are no electric field lines passing perpendicular through the area. So we have flux will be equal to 0. So theta is the angle between the two vectors E and delta S. If you need to look into the SI unit, in the previous section we know the electric field has a SI unit, Newton per Coulomb. This delta S is the area vector. So we have area Newton meter square. So we have flux SI unit as Newton meter square per Coulomb. It's a scalar quantity. So you know all about flux now. It is defined as a number of field lines passing perpendicular through a whole area, a given area like delta S. The magnitude is given by E delta S cos theta, where theta is the angle between the two vectors, electric field and area vector. Its SI unit is Newton meter square per Coulomb. If you look into your printed notes now, you will see the next topic is about an electric dipole. An electric dipole, like the name suggests, is a dipole, meaning you have a two polarity. That is, you have a positive charge Q and a negative charge Q separated by a very short distance, always represented as 2a. The distance is represented as 2a. So plus Q and minus Q, we have two equal but opposite charges separated by distance 2a, which is what you call as a dipole. Net charge on an electric dipole is therefore going to be equal to 0 because you have a plus Q. Like for example, if you have a plus 2 microcoulomb, you will also have a minus 2 microcoulomb along with it, which means the net charge of any dipole is going to be 0. Distance between them is what you call as 2a. The very next topic below that is another quantity called the dipole moment. Dipole moment, represented by the small letter p. P again is another vector defined as the product of any one of the charges. That means magnitude of the charge, plus q and minus q, both of them have the same magnitude. So magnitude of any one of the charges, product of that and the total distance between the two charges. Here again, the distance becomes a vector always directed from the negative charge to the positive charge. So your distance is a vector directed from negative to positive, because of which your dipole moment is also a vector whose direction is always from the negative charge to the positive charge. So dipole moment is a product of any one of these charges, because anyway both of them have the same magnitude, multiplied by the total distance between the two vectors. It happens to be a vector quantity because we have the distance here as a vector quantity, always directed from the negative charge to the positive charge. Its SI unit, very clear from the formula. The SI unit for charge is coulomb with a capital C, and the distance in meters with a small m. Make sure that you use a capital C, because if you write small c, then it becomes a centimeter. This is coulomb meter. Coulomb being the SI unit of charge, and 2A has an SI unit of meter. So that is dipole moment P, which is a vector quantity, directed always from the negative charge to the positive charge. So we've just finished 3 topics on page 3, electric flux, then electric dipole and dipole moment. What we now have, in this chapter we have 6 derivations, out of which 3 come under dipole. So we are now going to do the derivations based on these dipoles. There are 3 of them. The first one is electric field along the axis of an electric dipole. I'll write the heading on the board. It's there in your printed note. Electric field on the axis of an electric field, of an electric dipole, sorry. So this is what we're going to do, and for that please look into the figure in your notebook, in your printed notes that I've sent you. I have placed a positive Q here, and then at a distance 2A I have marked a negative Q. I have marked the center of the dipole as O, which means if this distance is A, then this half also will be another A, because the total distance we know is 2A. We are going to find out the electric field on the axis of this dipole. So this is minus Q and this is plus Q. Now I'm going to take a point, let's say point P, along the axis, which is at a distance x from the center of the dipole. So what we're going to do is find the net electric field at point P because of these 2 charges. So you will see that this point P is along the axis. Axis means the line joining the 2 charges. This line that I've drawn is what you call as the axis. So we have taken point P along an axis. So P is called an axial point for the electric dipole. The electric field will be the net field due to 2 charges, because this could behave as a source charge, thereby have an electric field here. And this could be also another source charge, providing an electric field here. And we will do the vector addition of the 2 electric fields, because electric field is a vector. The net electric field will be the vector sum. Now let us consider this as the source charge. Because it is a positive charge, I previously told you that all positive charges, the electric fields are radially away from it. So if I'm going to keep a plus 1 coulomb here, it means that this plus Q is going to repel it. So I'm going to mark this as the electric field E1, which is due to this plus Q charge. If you were going to write an equation for E1, you would write, your formula for electric field, I hope you remember, is 1 by 4 pi epsilon 0 Q by R square, where Q is a source charge. Do you remember what is R? R is the distance from the source charge to where you're keeping the plus 1 coulomb. So here it would be 1 by 4 pi epsilon 0. Your source charge is plus Q. So plus Q by R happens to be the distance from the source charge to where you are finding the electric field, meaning where you have kept the plus 1 coulomb. So that's our point P here. So that means we need the total distance from plus Q to point P. That is, this much is A. From here till here it is x. So we have an x plus A the whole square directed away from the plus q. Now we can consider minus q as the source charge. So because of minus q also there is going to be an electric field at point P. So if I am talking about a negative charge, naturally what should happen? Because of this negative q, it is going to attract the plus 1 coulomb, or the electric field lines due to negative charges are radially towards the source charge, inwards. So because of this, we have an electric field in this direction towards the source charge, because this 1 coulomb is going to be attracted by the minus q. So I am going to call that as E2, and that's going to be towards the minus q. If I am going to write an expression for E2, it's going to be 1 by 4 pi epsilon 0, the constant. My source charge is q. I don't have to put a negative sign because I'm only writing the magnitude here, not the direction. So the magnitude of the charge is q, and r as usual is the distance from the source charge to where you've kept the plus 1 coulomb. So my source charge now is here to plus 1 has been kept at point P. So this distance would simply be, this total thing is x, this is A. So from here till here, from minus q till that point P, it's going to be x minus A the whole square. Now, because the two electric fields are in one straight line but in opposite directions, how do you add vectors? If two vectors, in 11th standard we have learned addition of vectors. In addition of vectors, if two vectors are along the straight line in the same direction, you simply add them. If they are in opposite direction, you subtract them. If they happen to form, if they are not on the same straight line, then you can put them as sides of a parallelogram and use a parallelogram law of vector addition. Root of a square plus b square plus 2ab cos theta, that we did last year. So here, because they are in the same straight line and because they are opposite in direction, we will subtract the two. In this, which one do you think will be greater in magnitude? Naturally, it has to be E2 because it's an inverse square law. Your electric field is inversely proportional to square of the distance from the source charge to that point P. So you will see minus q is closer to point P. So obviously the electric field due to minus q is going to be a stronger electric field. So I'm going to write electric field E net. Electric field E net is equal to the larger one, E2 minus E1. And that's going to be equal to 1 by 4 pi epsilon 0 q by E2 was x minus a the whole square minus 1 by 4 pi epsilon 0 q by x plus a the whole square. I can take q by 4 pi epsilon 0 outside, and in the bracket, I think it's not clear to you. So I will take the net electric field. I can take that q by 4 pi epsilon 0 outside. Inside the bracket I have 1 by x minus a the whole square minus 1 by x plus a the whole square. Is that clear to you? Okay. Yeah. Then I'll take, this is a plus b into a minus b, so that will be a square minus b square. I'll cross multiply, so we have q by 4 pi epsilon 0 bracket. In the denominator, a minus b into a plus b will be x square minus a square the whole square, because there's a whole square here. Then if I take this side, it will be x square plus a square plus 2ax. And this, if I take here, it will be minus x square minus a square plus 2ax. Is that clear? Okay. 2ax, in which this x square and this will get cancelled, a square and a square will get cancelled, but we have a 2ax here and a 2ax which will add up to give you 4ax. Please look into your notebook, you will find that there. So the next thing we'll do is, so after cutting off that x square and a square, what we have is E net, which I will call as the axial field, because we are finding the electric field along the axis of the electric dipole. So this will be Q by 4 pi epsilon 0. We had a 4ax. If you, the previous step, if you look into your notebook, is 2ax plus 2x by x square minus a square the whole square. This 4ax I can split and write as 2 into 2x, 2a into x, because this is 4ax. Why I did that is because this q into 2a, in the previous topic I told you is dipole moment, so that I may write this as 1 by 4 pi epsilon 0, 2 into this q into 2a I will multiply and write it as a dipole moment, into x by x square minus a square the whole square. This is your equation for E axial, meaning the electric field along the axis of an electric dipole. Now this is your final formula, where, as you know, 1 by 4 pi epsilon 0, its value is 9 into 10 raised to 9. We started that in the first topic I told you under Coulomb's law. Then P is the dipole moment, which is the product of any one of the charges of the dipole into total distance between them. X is the distance from the center of the dipole to the point P where you're finding the electric field, and this is what we have. But your final formula, we will take a special case where you take the point P to be very far away, so that this x that we are talking about, this distance x, is much greater than this a, because dipoles are normally very short. So a being much lesser than x, you may neglect this a in the formula, in the denominator, which means x square the whole raised to square will become x raised to 4. So I am now going to take a special case. That is, for your special case, we have x much greater than a. Therefore, E axial is going to be equal to 1 by 4 pi epsilon 0 2px by x raised to 4, because I have neglected the a square in the denominator. So this, if I cancel, I will have finally E axial equal to 1 by 4 pi epsilon 0 2p by x cube. This is a vector whose direction will be the same as the dipole moment, the vector dipole moment. See, now we know here the net electric field means it's the net field due to two fields. We have E1 and E2, of which E2 is greater. Because E2 is greater, the net field will be in this direction. So E axial is in this direction, that is towards the left. Dipole moment, I already told you, is directed from minus q to plus q. So we have dipole moment also in the same direction, minus q to plus q. So we know E axial and the dipole moment in this case are in the same direction. Along the axis, directed from negative to positive, and the magnitude is given by 1 by 4 pi epsilon 0 2p by x cube. This has the value 9 into 10 raised to 9. P is a dipole moment, which is a product of q into 2a. X is the distance from the center of the dipole to point P. I'll close this session now. You will please go through your printed notes and learn the derivation for E axial of an electric dipole. Bye.